These notes are for AP Calculus AB. This is the start of Unit 8, on which we'll be covering special derivatives and integrals. 8.1 is on the natural log function. So I'm going to go over the graph, some properties, and what we'd like to do is learn how to take the derivative of the natural log function. So we're going to start with the graph. Of natural log x. All right, so we start with the fact that natural log x is just the reciprocal function of e to the power x. So any base to the power x, we'll start with e to the 0 power is 1. Anything to the 0 power is 1. E to the first is going to be e. So you might need to remember that e is a little bit, well, it's 2.718 and so on. It's close to 3, so 1, 2, 3. So e to the first would be about here, e squared, and it just builds up. So it's going to look like 2 to the x or 3 to the x and so on. Now, because the two are inverse functions of one another, we want to take e to the x and reflect it over the line y equals x. So the point 0, 1 becomes 1, 0, and the point 1e becomes e1. And we do this with all their coordinate pairs. And we end up here with the natural log of x. So it's important to note that it's still a growth curve, just like e to the x is growth, except it's just growing a lot more slowly. You'll also notice their asymptotes change places, whereas e to the x has an asymptote along the x-axis. The natural log of x has its asymptote along the y-axis. All right, so there are some properties about logarithms that we're going to review. The first one is that the natural log of 1, or really log 1 with any base, is 0. The natural log of a to the power x can be written as x times the natural log of a. So this was a power property. Third, the natural log of a times b expanded into the natural log of a plus the natural log of b. And so these were all properties we did last year. We just did them with all kinds of logs. Log base 10, log base 3, log base 12, log base 7, except now we're really only focusing on natural logs, which is our log with a base of e. Okay. The reason why we focus on it is because it has a very nice derivative. And so anytime we run into a logarithm that does not have a natural log and we want to take its derivative, we're going to make it a natural log first. And we can do that with the change of base formula. So I don't think you'll need that on this assignment, so I think I'll wait to introduce that one in the next objective. So right now, we're going to move on to the definition of natural log x. So it's given by the integral 1 to x of 1 over t dt. So hopefully that looks a little bit familiar here with the mixture of the variables. So what happens when we take this and we apply the derivative to it, right? That's going to be our second fundamental theorem of calculus. So if we take the derivative of each side, then we're taking the derivative of our integral. And you'll remember that our second fundamental theorem of calculus tells us to take x, replace the t, and then we multiply by the derivative of x. In this case, it would just be 1. So let's imagine if this were more than that, we'd want to multiply by its derivative. So 1 over x, yes, is the derivative of natural log x. But what if it's more than just an x? You want to make sure you multiply by its derivative. So if it's more than just x, if x is really an x squared plus 3x minus 9, or if it's a sine of x squared, whatever is inside of the natural log function, we take 1 and divide it by that value, and then we multiply by the derivative of that value. And so this is the definition of the natural log of any value. And so this is a very formula-heavy unit. So in Unit 8, we will be learning 10 different special derivatives and integrals. This is the first one that we'll be using. So all of my examples that I have now for this objective will just be using this formula and maybe some of the properties here to help us. All right, so it's wanting us to find the derivative and then simplify, and we'll either take the derivative and simplify after if we can, or we might want to consider simplifying before we take the derivative. So that will just depend on each problem as it comes. So example number 1, we have y is equal to the natural log of 3x. So in taking the derivative of y, we identify the piece that's inside, so the u value, so that's 3x. So following my formula, the answer is 1 over the stuff inside, so that's 1 over 3x, times the derivative of 3x, so times the derivative of u. The derivative of 3x is 3, and this simplifies to 1 over x. Number 2. All right, so simplifying with log properties, if I can simplify first, I would look to see if I could separate this in any way, but you'll remember with my log properties, there's only multiplication and division, besides having the exponent or a value of 1. So there's no addition inside of a log that I can expand this into 2 separate terms. So what that means is we can't simplify first. We just have to start by taking the derivative. So I'm going to identify x squared plus 1 as my u value. The formula says to take 1 and divide it by the u term, x squared plus 1. And then I want to multiply that by the derivative of the u term. So I want to multiply this whole thing by the derivative of x squared plus 1, which is 2x. And it doesn't look like I'm going to be able to reduce anything. So we're just going to write our answer as 2x divided by x squared plus 1. So nothing happens here with x squared plus 1. There's no factors. There's nothing that I can reduce, and this is my answer. So some problems won't simplify much. All right, on problem number 3, we have a square root symbol. So that's actually the same thing as having an exponent. So I could rewrite this, the natural log of 3x plus 2 to the power 1/2. Now, my power rule, that property I wrote down above, says that I can pull that 1/2 power in the front. So I'm going to write it as 1/2 times the natural log of 3x plus 2. Okay. Now, I haven't taken the derivative yet. I rewrote it and rewrote it. So now we want to take the derivative. 1/2 is just our coefficient, and we just keep the coefficient going along with us. We'll just take the derivative of the remaining piece like we've been doing with the last two problems. So dy dx, we're going to keep that 1/2 out front. Okay, and be really careful here. The derivative of a natural log is always 1 over. So 1 over whatever's inside. So the stuff inside is 3x plus 2. And then I want to multiply that with the derivative of 3x plus 2. The derivative of that is 3. So now putting it all together, I've got a 3 in the numerator and 2 times 3x plus 2 in the denominator. None of that will reduce. Nothing else can be factored. So this is my answer. Okay, this problem has a lot going on. Imagine if you just started with the derivative rule here that I gave you to do 1 over everything inside. So already you've created like a really big fraction, and then you want to multiply by the derivative of what's inside. The derivative of the inside stuff, you're going to use quotient rule. You've got chain rule as well as taking the derivative of a square root. That's a really messy derivative. You can do it that way, but I definitely don't recommend you do it that way. We're going to start by simplifying first with our log properties. So similar to what we did in problem number 3, except we've got a lot more we can do here. So the biggest thing first is this quotient. So we're going to take that last property that takes the quotient and divides it into the natural log of the numerator minus the natural log of the denominator. So this becomes the natural log of x squared plus 3 squared minus the natural log of root x squared plus 4. Each of them now have an exponent, and I can use my power rule, like in number 3, and bring that exponent in front. So the first one here, we bring 2 in front, natural log of x squared plus 3 minus square root is a half power, so 1/2 natural log of x squared plus 4. All right, so I've rewritten g of x finally to here. So now I'm ready to start my derivative. So I keep that coefficient 2. We multiply it with the derivative of our natural log, which is 1 over everything inside. So 1 over x squared plus 3, chain rule, times the derivative of what we just wrote here. So the derivative of x squared plus 3 is 2x. Okay, we do the next term, minus, keep the 1/2 coefficient, times the derivative of our natural log. We have 1 over x squared plus 4 times the derivative of x squared plus 4, which is 2x. So there's a little bit of reducing I can do here with the 2's. But other than that, it looks like our answer is just going to be combining our terms here. So I've got 4x over x squared plus 3 minus x over x squared plus 4. And those denominators are different enough and messy enough, and if we multiply it across to kind of get the common denominator and work it out, it'd be a lot more work than we need to do. So we are just going to leave this one with this answer. So I want you to think about back to the beginning when if you didn't rewrite it with log properties first, how much messier this derivative would have been, how many steps it would have been. You've got chain rule. You start with the quotient rule when you do the derivative of the top, chain rule, derivative of the bottom, chain rule. You've also created a giant complex fraction. By using the log properties first and breaking it up into separate parts and then doing our derivatives at the end, it was actually really simple. Okay, and that's what we want to do. We want to note anything that's easier to do. So if you can use those log properties first, always use those log properties. So let's look at example 5. y is equal to the natural log of x. So this looks a little bit weird, but focus on the outside natural log has something inside of it. So this is our u term, okay? So just like in our formula here, this is the u term. So the derivative of y is 1 over what's inside, so 1 over ln x, times the derivative of natural log x. So the derivative of natural log x is 1 over what's inside, 1 over x, times the derivative of x, which would just be 1. So right here, we get 1 over x times ln x. And that is a pattern that you'll see appear a lot, especially when we get to the integration part with logs. So look out for this pattern. I think I just have a couple more that I want to show you. So number 6, y is equal to the natural log of x cubed. Okay, now this isn't our power rule because the power rule only works if you don't have parentheses. So when that exponent is affecting only the thing inside of the log, and that's not what's happening here. This is really the natural log of x 3 times. So I can't use the power rule property to bring the 3 out front. Okay. Instead, I'm going to just start taking my derivative because the outermost piece is a power rule. So really, this is taking the derivative of u cubed. And the derivative of u cubed is 3u squared. It just so happens that our u term is natural log x. So power rule first. So we bring 3 out front, we drop the power by 1 to 2. Now I can move inside because of the chain rule and start taking the derivative of my natural log x term. So the derivative of natural log x is 1 over whatever's inside times the derivative of what's inside. Okay, so we end up with something that doesn't simplify either, which is fine. We have 3 quantity natural log x squared divided by x as our answer. So just to show you that your derivative might have a log in it, but it might not start with taking the derivative of the log itself. Okay, but instead, this one started with that power rule. So number 7. All right, so we want to do the same thing here. This cube root is a 1/3 power, so our power rule says we can bring it out front. So that's a 1/3 times natural log of x minus 1 over x plus 1. Well, from there I can use my quotient rule and split this apart. So this is now 1/3 of natural log of x minus 1 minus the natural log of x plus 1. You'll notice that because it created a binomial from a monomial, so 2 terms from 1 term, I have to keep that 1/3 with the brackets here because that 1/3 affects the whole thing just like it did in this step before. So to take the derivative here, we'll keep that 1/3 coefficient and then start taking the derivative inside. So the derivative of any natural log is 1 over whatever's inside times its derivative, 1. And then we repeat that over here, minus 1 over whatever's inside, x plus 1, times its derivative, 1. And then here, this isn't so bad to get a common denominator of x minus 1 and x plus 1. So I'm going to leave my 1/3 out front here, my common denominator of x minus 1 times x plus 1. So this fraction is an x plus 1, and this one needs an x minus 1. You distribute that negative, so you end up subtracting x minus x, and then 1 plus 1 is 2. So I end up with a 2 on top, and we have a 3 on the bottom, x minus 1, x plus 1. Okay. You won't always need to simplify them so much, so you'll notice that number 4 problem that we left it without getting the common denominator because it looked like it was going to be a bit more messy. This one was a little bit simpler, so we went ahead and got the common denominator. All right, that ends our 8.1 notes for today.